Hey, welcome back. In this video, we're going to talk about the comparison test, really the first part of the comparison test. And so to get us started off, I'd like you to consider the series sum from n equals 1 to infinity of 1 over n squared plus n. Now, if I write out the first few terms, this is what I'm going to get, 1/2 plus a 6th plus a 12th plus a 20th. Now, this isn't a p-series, okay, but it's close, okay? It's 1 over n squared plus n. I mean, that looks a lot like 1 over n squared. Okay, so, it's pretty similar to this series right here. Same thing that I did up here. I wrote out the first few terms. I'm going to go ahead and write out the first few terms for this 1 over n squared series as well. So I'm going to get 1 plus a 4th plus a 9th plus a 16th. And there's an interesting comparison that we can make here. What I'd like you to notice is that the terms in this second series are bigger than the corresponding terms in the first series up here. What do I mean by corresponding terms? Well, if I look in this second series where I've got n equals 1, 2, 3, and 4, and compare that to the first series up here, where again I've got n equals 1, 2, 3, and 4, the terms in the second series are bigger, okay? 1 is bigger than a half, a 4th is bigger than a 6th, a 9th is bigger than a 12th, a 16th is bigger than a 20th. Okay? In general, it's true that 1 over n squared is greater than 1 over n squared plus n. Right? That makes sense. If the denominator of a fraction is bigger, that makes the fraction as a whole smaller. Okay? So, if the individual terms are less in this first series than the individual terms in this second series, then adding them all up is also going to be smaller. So it must be true that this sum of 1 over n squared, that sum must be bigger than the sum of 1 over n squared plus n. Why is that the case? Well, the terms in this series are bigger than the terms in that series. Okay, take a look back here. 1 is bigger than 1/2. 1/4 is bigger than 1/6. Okay? All of my terms here are bigger than all of my terms here. That means that this sum is going to be bigger than that sum. This should kind of make you scratch your head and maybe go, what's going on here? Can we use this? Turns out we can. First of all, I'd like you to recall that if a series converges, then the sum is finite, right? If any series converges, okay, this is just an arbitrary series, if that series converges, then I know that the sum is finite. Okay? Very important concept to remember. Now, this one series we were looking at, this 1 over n squared, that converges, okay? Because it's a p-series with p equals 2. Remember the p-test said that p had to be greater than 1, and 2 is certainly greater than 1. So I know that 1 over n squared, that converges by the p-test. Why? Because p is 2 and 2 is greater than 1. Well, that means that this series is finite, okay? It converges, so it's a finite sum. And we noticed this really interesting relationship here, this 1 over n squared, that series was bigger than 1 over n squared plus n. And of course, both of these sums are going to be positive. They're both greater than 0. I'm just going to throw that in there just so we kind of remember that we're dealing with positive things here. Okay, well, since this series, okay, this 1 over n squared, is bigger than my 1 over n squared plus n, and this series converges, okay, this series here is finite, that must mean that this other series, okay, this 1 over n squared plus n, must also be finite. Okay? 1 over n squared is finite, and that's bigger than this series. Okay? So a finite thing and something less than that finite thing, well, the thing that's less than must also be finite. Okay? Well, if that sum's finite, then that means that series must converge. This is basically what the comparison test says. Okay, specifically, I'm going to call this comparison test part 1. We'll get to part 2 in the next video. But if I've got two series, and those series have positive terms, okay, I've got a sub n and b sub n, two series with positive terms. Let's suppose that all of the a sub n's are less than all of the b sub n's. Well, if that's true, and my series of those b sub n's converges, then my series of a sub n's are also going to converge. Okay. Why is this the case? Well, remember, if b sub n converges, then that means this series is finite. Okay. Well, if all of the terms in my a sub n series are less than all of the terms, the corresponding terms in my b sub n series, then this sum is going to be less than that sum. Why? Because the terms here are smaller than the terms there. Okay? And if this one converges, then this sum is finite. Well, this sum is less than that sum. And if this one's finite, and this one is less than that one, then this one must also be finite. If you want to say this in words, you could say that a positive series whose terms are less than the corresponding terms of a positive and convergent series is also convergent. Okay, that's kind of a mouthful. I like to think of it as a series that's less than a convergent series is also convergent. Okay? Or you can just say less than convergent means convergent. Alright, let's look at some examples. We're just going to test each series for convergence. Okay, we're going to use the comparison test. First one, let's look at the sum from 1 to infinity of n over n times n plus 1 times n plus 2. Okay, I want to compare this to a p-series. And what I'm always going to do when I'm looking for, what should I compare this to, I'm always going to look at n behavior. Okay, I'm going to think about taking the limit as n goes to infinity. This one's pretty easy. I can actually cancel out that n on top with one of the n's on the bottom. Okay, so now I've got 1 over n plus 1 times n plus 2. And at infinity, that's going to behave like 1 over n squared. Okay. Of particular interest is the fact that this is less than 1 over n squared. Okay, the denominator is bigger. That makes the fraction smaller. Okay, so look at n behavior, and you want to find a p-series that you know it either converges or diverges. In this case, that series 1 over n squared converges by the p-test because p is equal to 2, and 2 is greater than 1. Okay, that's the condition for convergence for p-series. My power must be greater than 1. Okay, 2 is greater than 1. So this p-series here converges. Well, that series converges. This series is less than that series. And that's because of this relationship that I've shown in this line right here. The general term for the series that I'm given is less than the general term in the series 1 over n squared. Okay, that makes this series less than that series. Therefore, I know that that series I started with, that series is going to converge by the comparison test. Let's take a look at another example. Let's look at the sum from n equals 1 to infinity of 1 over n cubed plus 11. Well, again, looking at n behavior, this is going to behave like a 1 over n cubed. And of particular importance is that this is less than 1 over n cubed. Okay? And I know that 1 over n cubed is convergent because it's a p-series with p equals 3. Okay? And 3 is bigger than 1. Okay, well, if the general term in this series is less than the general term in that series, that means this series is less than that series. Okay, and this series converges, that means this series also converges. Why? Well, that series converges by the comparison test. Alright, let's take a look at one last example. Now this one's a little different, okay? Cosine squared of n over n squared. Well, I can't just compare that to a p-series right off the bat because I've got this cosine squared on top. But here's what we can do with that. We know that cosine is a function that's bounded between -1 and +1. Okay, cosine, no matter what angle you pick, it's never going to be outside of those values. Okay, we also know that squared things are positive. So if I look at cosine squared, all of my negative stuff is going to go away. So that means I can bound cosine squared between 0 and 1. Well, if cosine squared is always less than or equal to 1, then that means the general term in this series up here, that's always going to be less than or equal to 1 over n squared. Okay, cosine squared is always less than or equal to 1. Denominators are the same. Okay. Well, I know that 1 over n squared converges by the p-test, because that's a p-series with p equals 2, and 2 is bigger than 1. Okay. Well, if this series converges, and this series is bigger than that series up there, that means the series that I started with must also converge. So therefore, that series I started with converges by the comparison test. Okay. All of these examples, what we're doing is we're taking the series that we're given, okay, and we're trying to say that it's less than some convergent series. Okay. So always remember, less than convergent means it's convergent. Okay, less than convergent means it's also convergent. So if you can establish that relationship between two series, then you can use the comparison test to help tell you about convergence. Alright, that's it for this video. We'll be back later with part 2 of the comparison test.